Hi everyone. In this video I am going to derive an expression for the moment of inertia. In the last video of our introduction to rotational spectroscopy, we discussed why it is necessary to consider a polar molecule. So to derive the expression of moment of inertia also, we are considering the same polar diatomic molecule which is rotating in an axis which is passing through the center of gravity of the molecule. So in this case, we have two atoms. One is having a little bit higher mass, let that be of m1, and the other is of smaller mass, which is of mass m2, and the bond which is connecting the two atoms, let it be R. So in such cases where one mass is heavier, so the center of gravity will be shifted from the middle point to the point where there will be of higher mass, or we can say at the center of point, if I am going to keep an axis, with that axis this molecule will be rotating. So let this be our center of gravity, and the distance from the mass this m1's center to this point will be our r1, and from here to the center of m2 will be our r2. So according to the definition of center of gravity, you can write m1 r1 is equal to m2 r2. So we know R is the equilibrium bond length. So we can write this R is also equal to sum of R1 plus R2. So we can write it like this: R is equal to R1 plus R2. Let this be our equation number 1 and this be our equation number 2. Now in real life, bond is something which can rotate or vibrate, or it is something which is having motion. But when we are considering a rigid rotor, we are restricting all sorts of motion possessed by a bond. That means a rigid rotor is a molecule which rotates such that its internuclear axis or internuclear bond, this will not be getting disturbed, or when this is under motion, there won't be any stress of rotation happening towards this axis. So there comes the next point which we have to follow to proceed our definition, that is the moment of inertia. In earlier classes you might have studied about moment of inertia, like mass of the body multiplied by square of a distance from the center of rotation. So it's actually an expression. This expression I have told is tendency of body to resist the angular acceleration possessed by that. So you can write an expression for that. We are not going much deeper to moment of inertia and its definitions. So as I said, moment of inertia is I into mr square. This is the basic definition you should know. So from this definition you are going to start our derivation. So in this case, what I am going to do is I is equal to m1 r1 square, like this m1 into, according to the definition, mass into r square. So here in this case m1 into r1 square plus, because this is a system, you have to consider both this mass and this mass also. So this will be m2 into r2 square. So it will be m2 into r2 square. Now I am going to expand this square terms. So it will be m1 r1 into r1 plus m2 r2 into r2. So let this be our equation number A. Now I have already defined what is m1 r1 and what is m2 r2. So now I am going to change this m1 r1 with m2 r2 and this m2 r2 with m1 r1. So I am going to rewrite the expression. This m1 r1 is equal to m2 r2 into r1 plus this will be same. This M2 R2 is equivalent to M1 R1. So instead of this you can write M1 R1 into the same R2. So now you will be getting R1 R2 and here also R1 R2. Now you can take that R1 R2 common. So here you will be left with M2 and here you will be left with M1. Let this be our equation number B. Now what you are going to do is, here you have written R is equal to R1 plus R2. So when I am going to write this equation, I am going to rewrite this equation here itself. R2 is equal to, in terms of R2, when I am rewriting here, R2 is equal to, now you have to take this R1 term to left hand side. So it will be R minus R1. Now I am going to change this R2 term in equation number 1. So when I am going to rewrite this equation, so here you can replace this R2 with this one. So when I am rewriting or substituting, you can give an equation something, this star or something. When you are going to substitute the star equation in equation number 1, you will be getting an expression like M1 R1 is equal to M2 into R minus R1. Now you can open the bracket. So M1 R1 is equal to M2 R minus M2 R1. Now we are going to take this term to the left hand side because you need an equation of R. So M2R is equal to M1 R1. This plus will be, this minus will be plus M2 R1. Now we are having R1 in both the terms. So you can take R1 as common. So when you are taking R1 as common factor, after this M2R will be equal to, R1 will be common, then M1 plus M2. So you can take the expression for R1. R1 is equal to, you have to take this one to the left hand side, so this will be going towards the denominator, M2R divided by M1 plus M2. The same way you got the expression for R1, if you are replacing R1 here, you will be getting the equation of R2. The same way only you have to proceed. So now I am going to rewrite this expression in the next side. So the expression will be R1 is equal to M2R divided by M1 plus M2. Let this be of our equation number D. And if you are replacing R1 instead of R2, from R2 you got R1. So here you will be getting R2 is equal to M1R divided by M1 plus M2. Let this be our equation E. So now what you have to do is, you have to replace, here you are having, in this expression you are having R1 and R2. Now you have to replace, in this equation you have to replace the R1 and R2 here. So I'll write that expression. Here you are having I is equal to M1 R1 square plus M2 R2 square. Now you have to replace this R1 with this expression. So your equation will be M1, instead of this R1 you have to substitute this one. So it will be M2 R divided by M1 m1 plus m2 the whole square plus m2, instead of this r2 you have to keep this one, m1 r divided by m1 plus m2 square. Now upon opening this square terms, you will be getting m1, m2 is in the bracket, so it is having square, r square divided by m1 plus m2 square plus m2 m1 square r square divided by m1 plus m2 square. Now you are going to take m1 m2 r square divided by m1 plus m2 square as common. So when you are going to take m1 m2 r square out, you will be left with, now you are going to take that common, m1 m2 r square divided by m1 plus m2 whole square common. You will be left with one m2 term, and here when you are taking, you will be left with one m1 term. So this will be in the bracket. Now what you are going to do is m1 m2 divided by m1 plus m2, you are going to cancel this one, so you will be left with this kind of equation. You have to carry the I over everything, and so you will be getting an expression like this. And now what you are going to do is you are going to replace this m1 m2 divided by m1 plus m2 with a special character mu. So you will be getting the required expression. So the expression of moment of inertia is now this one, I is equal to mu r square, where mu is equal to m1 m2 divided by m1 plus m2. This is known as the reduced mass of a molecule. So this is all about the expression for moment of inertia. I hope all of you understood what is the concept behind it and what are the steps we have to follow. Now you have to just practice it 1 or 2 times for your board exams and all, like BSc, MSc exams. Or for the exam point of view, if you want to clear this concept for the GATE exam or NET exam, you just have to memorize these formulas, the important formulas. So in the next video, we will be deriving expression for rotational energy regarding the allowed energy levels. We'll have a discussion. Thank you.